Red rock. What is it? Well, it's a rock. But why is it? Well, if you've ever looked at a map of the US, you've probably noticed that glaring sea of it somewhere between southern Utah and northern Arizona. So, how did all that red rock get there, and what inherently is that red rock?
Colorado. It invokes images of mountains, skiing, and meadows aplenty. But what if I were to tell you that the state of Colorado only has a tiny sliver that lives up to its name?
Colorado means colored red, which comes from the color of the Colorado River and not so much the landscape. But today we're going to talk about the real colored red landscape of the US and explain how it formed. You see, red rock, in most cases, when we're looking at that big pit in southern Utah and northern Arizona, is largely made out of sandstone. What is sandstone? Well, it's exactly what it implies. It's a bunch of sand grains that have been compressed together and lithified, which means compacting into a solid rock, and thus creates sandstone. But what is in this sandstone? Well, believe it or not, it's mostly quartz. Yes, the same stuff that your friend that's a little weird that rubs like a genie lamp hoping that it's going to give them luck is the same stuff that you can find in a handful of sand pretty much anywhere. Why is it red though? Well, it's red mainly because of iron, specifically iron oxide, and we'll talk about that a little more later.
While a lot of amazing rock exposed in these regions via the wondrous power of weathering and erosion are nearly 2 billion years old, we are going to start our journey around 300 million years ago. The majority of the western US is underwater at this point, and thus begins millions of years of mountain building, eroding, seas advancing and depleting, and just in general a very active environment. These advancing and retreating seas create something called a regressive-transgressive sequence. In a regressive sequence, seas retreat. In these sequences, sandstone overlaps deeper ocean shale and limestone deposits, and in a transgressive sequence where ocean levels rise, the opposite happens. Essentially, a lot of sandstone, shale, and limestone is deposited over this period. These rocks were then pushed up and eroded in a series of 3 different orogenies, orogeny meaning mountain building event, starting around 180 million years ago. These orogenies, in order, were the Nevadan, the Sevier, and finally the Laramide orogenies. The eroding mountains from the Nevadan and Sevier orogenies were exposed to a lot of oxygen, and this will be important later. At this time, Earth's atmosphere is very oxygen dense, and the whole area is actually closer to looking like modern-day Costa Rica, so there's lots of water and lots of trees. As the plate containing this area began to drift further north and large mountains formed, they created a rain shadow with a lot of downwind. This downwind picked up sediments which were then blown into large sand dune fields, exposing them further to oxygenation and erosion. It's time we talk about colors.
So let's talk about why that red rock is red. We got to go back to talking about iron. See, iron is something called a chromophore, which means that even in really, really tiny trace amounts, it can affect the color of an entire mineral. Iron oxide is the thing that we want to talk about especially. You see, when iron combines with oxygen, it rusts, giving us that really amazing red rock color. How did this iron end up rusting? Well, usually it's when it mixes with water. So anywhere during the laying down process of this sand, like when it deposited in those shallow seas we talked about, or when it got lifted up in those mountains and rained on and eventually eroded and weathered. All of these things subject the rock to water, which in turn oxidizes the iron within it.
Exposed to a lot of water and hydroxide, it can turn yellow. If it's partially exposed to these things, it can turn brown. If not exposed to much oxygen, it can appear blue or green. A lot of oxygen, it can be black.
Just for some real-world examples, if you've ever seen an iconic beer bottle with that brownish-reddish color, why is it brownish-red? Well, they don't make it that way on purpose. It's actually because there's trace amounts of iron within the bottle that make the entire bottle that color,
even when there's very, very tiny amounts in the glass. And so, by that very logic, not every rock has to be sandstone in order to be red. In fact, these very rocks we've been showing in this video are mostly volcanic in origin. Now that we've established how our sandstone got its amazing red color, we need to talk about how it was uplifted and how it eroded to form the beautiful seas of red rock that we see today. Now it's time to talk about the last of the three orogenies I mentioned earlier. This one was known as the Laramide orogeny, and it's kind of a funky one. You see, the Farallon Oceanic Plate, as it approached North America, instead of colliding and subducting like you would traditionally see, it kind of held on and skimmed under North America at a flat angle, resisting melting along the way, until finally taking the plunge into the mantle several hundreds of miles into the North American plate. Now, all these scraping and shearing forces caused by the Farallon Plate on the overriding North American plate caused the lower part of the North American plate, known as the lithosphere, to weaken and break off in a process known as lithospheric delamination. This broken off chunk just sank into the mantle and caused a big mantle upwelling of magma that made its way up towards the North American plate. This caused a huge section of Earth to be uplifted several thousands of feet in some instances, creating the Colorado Plateau. Now let's go into some individual regions and cover specifically what took place. In Sedona, Arizona, intense fracturing and lingering seas like the Paragosa, which fostered very good environments for the formation of limestone, led to a uniquely cracked and limestone-rich environment. In the Grand Canyon, the uplift was quite dramatic, also paired with volcanism, and it began rapidly getting cut by several creeks in the large Colorado River, which had formed recently with the uplift of the Rockies. Zion National Park, on the other hand, was already slightly uplifted and had active creeks before the Laramide, but the further uplift strengthened the creeks and gave birth to the Virginia River, which led to very rapid and steep erosion, creating the magnificent rocks that we see today. In Capitol Reef National Park, the reactivation of an ancient fault shifted the landscape even further, creating a huge warp zone known as the Water Pocket Fold. In Arches National Park, softer rock was eroded faster than the rock above it, leading to the creation of natural arches and bridges. And in the aptly named Colorado National Monument, extreme erosion exposed the ancient billion-year-old Precambrian bedrock, which gives the landscape a very unique look. So even though this large area of red rock can be traced back to similar origins, how much it was uplifted, where it was uplifted, what direction it was facing, how much water there was, and many other factors led to the diverse landscape we see today. I'm here with Vicente. He helped me film this video, so thank you to him. I'm going to try to start posting a lot more. I know it's been a long time. I'm going to start trying to post every 2 weeks on Sunday, so come back here 2 weeks from now, and there will be another video up about Lassen Volcanic National Park, a super dope place that I am very, very excited to cover. And I will catch you in the next one. This is a blooper for anybody that makes it to the end. I'm not even sure if this is sandstone. I'm fairly sure this is volcanic rock, and I'm in California right now, not Utah. Thanks for watching.